This video discusses about examples about hypothesis testing in a linear mixed effect model. And we start by hypothesis test about the fixed effects of a linear mixed effect model. So in the previous example 2.21, we noticed that in our transformed height diameter linear model or linear mixed effect model, we had some slight relationship between the mean diameter of the plot and the random intercept, and therefore we have here updated the model so that we also include the mean diameter of the plot as an additional predictor to the model. And now we would like to test whether we have evidence against the hypothesis that beta 2 is 0, which was assumed in the previous model. And to do that, we can specify the following hypothesis matrix. So we set one parameter to 0, therefore we have only one row in this matrix, and we want to pick the second coefficient of the model, therefore we put number 1 to the second element of the matrix. And in R, in models fitted by using function LME, this test can be done in various ways. First, here we update the model LMM6 by including this mean diameter as an additional predictor, and then we save the new model to object LMM7. Then we specify here the contrast or hypothesis matrix L, and then we can do this using this ANOVA command, and we get the value where the denominator degrees of freedom are 1, numerator degrees of freedom are 1, and the p-value is 0.4717. We notice that this denominator degrees of freedom is 54 because now this predictor d mean is specified at the group level. So for every group or every sample plot of the data, or for all observations of the same sample plot, the value of the predictor is always the same, and therefore this denominator degrees of freedom is computed using formula m minus r minus 1, where m is 56, the total number of plots in the data, r is 1, the number of restrictions, number of rows in this L matrix, and then this 1 here is just to take into account the 1 degree of freedom that is used for estimation of the intercept of the model. The same test can also be conducted using the same ANOVA function, but using argument terms. So it means that we drop the second term from the model. Okay, to know what is the second term, we could first run this ANOVA function without this terms argument to see the order of terms in the model, and then see that which term we want to drop. And the result from this test is exactly same as before. So we see that the df and p value and everything is the same. It is doing the same test. We could also do the same by using this ANOVA, and type is marginal, which means that we are using the type 3 sum of squares, and then we are picking only the second row of that output, so we see the exactly same result again. Then a fourth equivalent way to do this same test is to make a t-test for the model. So we could just use function summary of the model and then select the fourth row of the summary, and then we see that we get a t-test which is based on this t-test statistic, and the df is 54, which is the same as before, and the p-value is the same as from the f statistic. And now it's important to notice that actually this t squared is f, so 0.72 to the power of 2 is equal to 0.47. So this t-test and f-test are t-test and two-shaded t-test and f-test, they are exactly the same. Okay, and then even though it's not recommended, we could also use likelihood ratio test to do the same hypothesis testing. But to do the likelihood ratio test for for fixed effects, we need to re-estimate the models using maximum likelihood, because the restricted maximum likelihood was used previously in model fitting. And then we can do the test by using the two-argument form of ANOVA, and what we get, the test statistics gets value 0.53, and the p-value related to that is 0.46, which is very close to what we obtained from the previous F or T tests, but not exactly the same, because now this likelihood ratio test, it is a different test. So the p-value from the test is different, but in this particular case at least, the F-test and likelihood ratio test results are very close to each other. The p-values are very close to each other, and the conclusion is the same, which means that d-mean is not needed in the model as a predictor in the fixed part. Okay, then we could also be interested into testing whether the mean diameter and the interaction between mean diameter and the tree diameter is needed in the model. So then it means that we would like to restrict the beta 2 and beta 4 jointly to 0. And this is now problematic for the F-test, because the denominator degrees of freedom for D bar is 54. So we have 56 groups in the data, but on the other hand, this product here gets a unique value for every observation of the data. So therefore, the denominator degrees of freedom for this is approximately the total number of observations in the data. So therefore, the F-test cannot be done. We could compute the F-statistic, but we cannot do the test, because the distribution of the test statistic under the null hypothesis is unclear, because we don't know whether we should use the denominator degrees of freedom for this or for this in the test. And therefore we are doing the Wald F-test, Wald chi-square test here instead. And it can be done in R using functions of package CAR and function LHT there, for example, can do that. And here we are doing that. So here we just specify the hypothesis matrix. Okay, first I do the ANOVA using the NLME ANOVA, but you see that it is not able to do anything for me. So therefore I switch to CAR here and then run the LHT, and then it gives me the result, which shows that chi-square statistics is 28 with degrees of freedom 2, and therefore the p-value is very low, which means that either mean diameter or the interaction between diameter and mean diameter are needed in the model as a predictors in the fixed part. Okay, then we might want to do some tests about the random part. For example, we might want to test whether the random slope is really needed in the model. Okay, our previous graphical evaluation clearly indicated that such is needed, but probably we would like to confirm that. So we can make hypothesis test using the null hypothesis that the variance of the slope is 0, and this assumption implicitly also means that also the covariance between the random intercept and slope is 0, or that covariance term is dropped from the model. And now we can use the two-argument ANOVA for that. So we update with another model, LMM8, that includes only random intercept at the plot level, and therefore now we have both element 6 and element 8 fitted, and now we are using the REML likelihood ratio test, because we are doing tests about the random effect part of the model, or random part of the model. Now the degrees of freedom difference between degrees of freedom in the models is 2, because now LMM8 has 2 parameters less than LMM6. The likelihood ratio statistics is 312. It is very different from what we, it is very far from 0, and the p-value related to that is very low. So it indicates that the random slope is also needed in addition to the random intercept. But now this test is problematic because it sets the parameter to the boundary of the parameter space. So especially it says that the variance is restricted to be to 0, which may not make sense. I mean, which of course it makes sense, but which is problematic from the point of view that this likelihood ratio statistic or test is valid only when the parameter is set to the interior of its parameter space. So therefore we might consider, we are not very sure whether we can trust on this p-value. Of course in this particular case this p-value is very well in line what we have already observed about the need for random intercept slopes in the graphical evaluations previously. But we can also do the same test by using parametric bootstrapping. So in parametric bootstrapping we generated a total of 1,000 simulated datasets by assuming that the null hypothesis is true, and then that is the way we obtained the distribution of our test statistics under the null hypothesis, and then we compute the likelihood ratio in our empirical data and observe that it gets value 313. It is not shown here, but it is the output from this command, so it gives 312.69. And now those 1,000 simulated values of the likelihood ratio statistics show our distribution of the test statistic under null hypothesis, and then we can compare that whether this value is very rare or exceptional in that sample. And here we see that distribution of the null hypothesis, the distribution of the test statistics under the null hypothesis, we see that the values range from 0 to 12 in this sample of 1,000 realizations, whereas our observation is somewhere very far because the value is 312. So therefore we are very far on the right hand tail, so this parametric bootstrapping also supports that the random slope is also needed in addition to the random intercept. Okay, but then in the previous test we did, they used this Pinheiro and Bates method for computing the degrees of freedom for the denominator degrees of freedom for the models that are defined in that are used in the model. But we could also take into do the less conservative Sutter-Waite or Kenvan-Rogers approximations for that, and that is not possible using models fitted using NLME package, but we can instead using package LMA4 and especially LMR test that builds a testing on models fitted using package LMA4 are something that we could use. And here we are doing that. So here we first refit model LMM7 using this LMER function. You see that the syntax in this model is slightly different from the other packages, so you see that the random effect part is included in the same formula as the fixed effect, but it is included within the parentheses. So these notations here means that we include random effects for random intercept and random coefficient for diameter at plot level into the model. And then we can do the ANOVA using Sutter-Waite formula. And for example, when we look at the p-value from the test about the need for d-mean, it is very similar to what we observed. Previously, I think the value was 0.4717 in the model that we fitted by using the Pinheiro and Bates method, whereas here in this Sutter-Waite formula it gives difference only in the fourth decimal. The Kenvat-Roger method is implemented below or in the next, and here we also see some change to the previous, but again the difference is only in the third and fourth decimals of the p-value. But okay, these adjustments make difference only with small data sets, so therefore it might be interesting to see whether they would make sense or make a difference if the data would be smaller. And therefore, for demonstration, we generate a new data set that is a sample from the original data but includes only 70 trees. And this is called now SPATI2 small data set, and then we refit the models using to that data and then do the same tests in that data set. And for example, about the d-mean, for example, the Pinheiro and Bates method gives p-value 0.19. The Satterthwaite formula gives 0.1933. So again, the difference is only in the fourth decimal, but the Kenvat-Roger gives clearly higher p-value 0.22, which is then much higher than in the other methods. But anyway, no differences in the conclusion related to these statistics in this particular case.